and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. I'm Ekaterina, and I would like to introduce our speaker today, Natalia Teplova. Natalia got her master's degree in plasma physics at Petersburg, St. Petersburg Polytechnic University, and then she entered to the PhD under joint program in Ioffe Institute in St. Petersburg in Russia and Lorraine University in France. The area of her interest was focused on the microwaves in plasma reflectometry and theoretical studies of this field. After the defense, she changed the field of her interest for lower hybrid current drive and joined the development of the fast ray tracing code incorporated to ASTRA code. Natalia is passionate about education, and she gives lectures on computer science and physics in several universities in St. Petersburg. She is also participating in teaching in the summer school of plasma physics in Petersburg, St. Petersburg Polytechnic University. Her career includes various achievements, such as winning ITER prize in the frame of EPS conference, but Natalia is successful not only in science, but also she enjoys rock climbing, and she climbed the Petit Dreux route Anouk in Alps, which is, by the way, 3,700 meters. And also she is proud of raising 3 kids. So without further delay, I give the floor to Natalia.
Good afternoon. I'm glad to meet you, and today I'm going to give you a short talk about low hybrid current drive. The frame of my talk is some introduction to this field. For non-specialists, I give you some basics of theory and give you some examples of results of simulations obtained at Ioffe Institute using our numerical codes, and some future ideas of the applications of these codes in future. So currently I'm a researcher at Ioffe Institute, and I give lectures on physics in ITMO University, and I give some lectures at physics and informatics at Peter the Great St. Petersburg Polytechnic University. And we have a lot of collaboration between all these institutes and universities. All of them are situated in St. Petersburg, Russia. I have mentioned here some of my colleagues because all the plasma physics subjects are collaborative and are the team projects. And of course, all of my work was not possible without my colleagues and members of our Tokamak teams at FT2 and Globus M2. The Tokamak toroidal magnetic trap has emerged today as a leading approach to controlling nuclear fusion for the purpose of electrical power generation. The central problem of controlled nuclear fusion is the confinement of charged particles. This problem can be reduced from 3D to 1D due to the current which encircles the torus hole. The current in a tokamak is produced by means of induction, where the plasma current acts as the secondary loop of a transport system. Such a construction is famous for the intrinsic pulsed nature of the tokamak device. The cyclic stresses lead to many problems, and some of them are failure of actual machine components and necessity of external storage of energy for the transformer. Due to such problems, we need to organize a steady-state operation of a tokamak. For steady-state operation, a method of continuously driving the toroidal current is essential. Moreover, the current in a tokamak is needed to create a rotational transform as well. To provide a toroidal current continuously, some toroidal asymmetry must be introduced into the tokamak. And how to operate the tokamak continuously? Nowadays, non-inductive methods of driving the current exist. Some of them are neutral beam injection, radial frequency methods of current drive, pellet injection, some asymmetric tokamak wall construction, and so on. All these methods provide toroidal asymmetry into the tokamak. I will focus in my talk on radial frequency current drive methods, especially the low hybrid current drive. For example, traveling waves may be induced in the tokamak in one preferable direction. These waves may be injected via a phased array of waveguides, for example, as low hybrid current drive green, or coil arrays at the periphery of the tokamak, or a horn waveguide may be tilted with respect to one toroidal direction. We shall examine shortly the physical basics for the current generation by low hybrid waves. This technique is believed to be the most successful radio frequency technique nowadays. The method is based on the effect of the transmission of a pulse by a slowed down radio frequency wave in the lower hybrid frequency range to the superthermal electrons due to Landau damping. Let's consider an electron interacting with electrostatic wave with frequency omega and wave number k. The electron travels with a velocity v. Electrons resonant with the wave, moving with velocity near the wave phase velocity, are pushed. The non-resonant electrons are not pushed. The push can either increase the particle velocity or decrease it. In general, the effect can simply cancel. However, the distribution function near collisional equilibrium is nearly Maxwellian in energy. Therefore, there will be more electrons that are pushed compared to those which are decelerated. This is the principle of Landau damping of the wave, and this is also the principle of the current drive effect. So here we can see in the figure that initial Maxwellian distribution has a high energy tail which produces the current in the tokamak plasma. I will give some theoretical basics of LHCD, some simple theoretical basics, of course, because in general the theory is much more complicated. Now we focus on those electrons which are pushed. I mean, we do not take into account the electrons which are decelerated. So we deduct this effect. In such approach, the electrons could not be slowed down, and the pulse is always lower populated states which take place in a electron distribution function. So let's consider an electron moving at some velocity. We need to push it for some additional increment velocity. This will produce an extra current, which is proportional to the increment velocity. The energy required for it is proportional to not only to increment velocity, but also to the velocity itself. And due to collisions, and this means that if extra current is proportional to the increment, but the energy required is also proportional to velocity itself. This means that it requires more energy to push faster electrons. However, we will see that the most effective approach is to push fast electrons. Due to collisions, the current is reduced with a frequency, collision frequency between electrons and ions. The power density dissipated is also proportional to this frequency. So we are able to calculate the lower hybrid current drive efficiency, which is inverse proportional to the collisional frequency. As soon as for superthermal electrons, the collisional frequency is inverse proportional to the cube of the velocity, we make a conclusion that the waves at phase velocity higher than electron thermal velocity, so for superthermal, are applied for pushing the electrons. And in this case, the efficiency will be proportional to the square of the velocity. This is a really huge value because the electrons possess the velocity about 4 or 5 thermal velocities. However, if we take into account the collisions, this will decrease the effect and the LHCD efficiency up to the factor of 100. The efficiency is also inverse proportional to the density of electrons. This leads to some limits in LHCD experiments, and for example, as it was shown on at the FT2 small Tokamak at Ioffe Institute, there is some limit for lower hybrid current drive. If we increase density, the effect disappears. Of course, this simple approach just gives an idea how the methods works. In this approach, we do not take into account the perpendicular velocity of the particles. We take into account only parallel velocity in toroidal direction. We do not take into account thermal effects, wave propagation in complex magnetic field geometry. The field geometry itself, of course, this is developed for traditional type tokamak, not for spherical tokamak. And the coupling between antenna and plasma is not taken into account. However, this approach gives an idea how the Landau damping and interaction between the particle and the wave works. I'm going to tell you the ideas for simulation and why do we need simulation for lower hybrid current drive. Usually when the experiment is set, no information on driven current radial distribution or some other parameters coming from experiment. So we have the only one parameter, the loop voltage drop, which gives an idea about the level of driven current. And that's the only parameter we can compare to simulations. And using simulations, we are able to calculate the efficiency of the method and select the conditions for future experiments. So the simulation is worth doing, and we are able to use various approaches for that. Here I show you the two branches of LHCD modeling codes. There are some more codes existing in the world, but the most spread are developed in the end of 20th century. The Genray code and CQL3D Fokker-Planck code. These codes are combining ray tracing and Fokker-Planck equation solution. And they are based on transp code. These codes solve Fokker-Planck in 2D and 3D. And the second system of codes was developed at Ioffe Institute in the end of 20th century. That's the fast ray tracing code, which has two versions, stationary and dynamic. And this code is based on ASTRA code and combined to some other codes. I will tell about this a bit later. The main difference between combined ray tracing Fokker-Plancks and full-wave Fokker-Plancks treatment has been found that that are thought to be related to interference effects, which are not accounted in ray tracing, that are present in the quasi-linear diffusion coefficient that is construction from full-wave fields. However, the full-wave approach requires huge power for calculation, and the ray tracing codes are more popular. They apply the solution of ray tracing equations for calculating the total current. The codes for simulation at Ioffe Institute are based on ASTRA code, which is one of the most complete codes for describing the inner region of the tokamak and is widespread among plasma physicists. This code calculates the temperature profiles of electrons and ions and their concentration, the neutral yields as a result of the two molecular reaction, and determines the efficiency of plasma heating. The astronomical code is designed to carry out an individual calculation of the evolution of thermal energy and the colloidal magnetic field in a tokamak plasma, provided that the position of plasma boundary is specified. And the latest version, Astra 7, gives a good result, especially for spherical tokamak. The main functional feature of Astra code is the availability of a simple set of source data, visualization, good visualization of calculated results in combination with the high speed of obtaining results. And the module FRTC, it's self-consistent code, can be used without Astra, but based on Astra incorporated to Astra code. This code allows to perform time-dependent calculations. This code was developed by two physicists, Alexander Savelyev and Alexei Pilia at Ioffe Institute, and written in a Fortran language incorporated to Astra code. The algorithm is well known and based on the combination of Fokker-Planck equation solution and ray tracing method. I would like to underline that the Fokker-Planck equation in the code is 1D, so it is solved in 1D, not taking into account the perpendicular effects. However, when we perform calculations for slow waves, this approach is quite strict and careful. In the present version of the code, the rays are considered using the cold plasma approximation. The power is divided into several beams and calculated in parallel with the ray tracing. And diffusion coefficient, electron distribution function, and error of power are calculated. The system works the following way. So I will tell that almost all ray tracing and Fokker-Planck codes work in the same way, in the same manner. So the Astra inputs are well known. So we put to Astra temperature and density profile and current plasma current evolution and input power. Then for every time step, Astra and the module FRTC exchange the parameters, and for each time step, the FRTC code solves the ray tracing equations. After that, the diffusion coefficient is calculated, then puts this diffusion coefficient is used for Fokker-Planck equation solving, which results in a distribution function, which is then used to calculate the current, and the current returns back to Astra. When this cycle is finished, finally we obtain the observables to compare to experiment. The only observable is the loop voltage, and a lot of quantities not measured in experiments, for such as distribution function of electrons for each time and radial position and velocity, lower hybrid current density, ohmic current density, total current, electric field distribution, and effective charge. To calculate the input power spectrum for given density, radial distribution, and magnetic field profile, we use a special model GRIL, which is called GRIL 3D, developed as well at Ioffe Institute. Some theoretical basics which explain how the code works. For ray tracing, we describe this procedure, which solves numerically the following system of canonical equations, describing the propagation of a separate spectral component of the launch spectrum. The Hamiltonian is usually taken in the form of a lower hybrid waves of the homogeneous plasma dispersion relation for lower hybrid waves. But this Hamiltonian is written for traditional type tokamak. In case of spherical tokamak, we use a corrected dispersion relation taking into account the gradient terms. These gradient terms take into account the curvature of magnetic field. At Globus M2 tokamak, as soon as it's a spherical tokamak, the angle between the magnetic field and the toroidal direction is about 30 degrees, and it's a lot and requires the gradient terms added to the Hamiltonian. In the right lower corner, this figure shows the example of ray trajectories calculated by ray tracing model of the FRTC for Globus M2 tokamak. The power injected to the tokamak, the example of a power spectrum for Globus M2 tokamak calculated using real 3D model is shown on the right side. This power is divided on several beams, and for each beam is calculated in parallel with the ray tracing based into the ratio which is calculated for each beam, for each ray. From these equations, calculating the RF power using 3D code, we determine the diffusion coefficient, quasi-linear diffusion coefficient, which is used further for solving the Fokker-Planck equation. Here I show it in red. To calculate the electron distribution function, the 1D Fokker-Planck kinetic equation for the fast electrons is solved in the following form and standard notations. I would like to underline that this equation is written for electric field as well, and it takes into account electric field, that inductive electric field is present and can play a noticeable role in the lower hybrid current generation, especially during the transition to the stationary stage in small tokamaks. It's not that important when we apply the code for huge tokamaks, like for example jet, but in case of small tokamak, we need to solve this equation taking into account the electric field, and as well as its the time evolution of the electron distribution function. This comes from the fact that the duration of radio frequency power pulse in small tokamaks, for example, in the FT2 tokamak, is only 6 microseconds, which is almost equal to the time at which the steady state distribution of fast electrons is reached. So there is no steady state. That's why these two formulas that you see on the screen are not applicable. That's the solution of a stationary Fokker-Planck equation, and these formula are no more applicable, and we need to solve the time-dependent Fokker-Planck equation, and we need to find its time solution. So under these conditions, the stationary solution is not valid, and the time evolution of electron distribution function, which of course results in changing the total current, this time evolution must be taken into account, which is done numerically in the present, so in this work. In the end of my talk, I give you some examples of modeling for small tokamaks, which are situated at Ioffe Institute. The first one is FT2 with a big radius about 55 centimeters and small radius 8 centimeters. This is a tokamak of classical type, toroidal machine. So you see the time evolution of temperature and density profiles in the screen during the injection of a radio frequency power. The power spectrum injected to the FT2 tokamak is shown on the left figure. The spectrum can be launched with a different phasing. I give you an example with a phasing in the direction of the current. So that's co-current direction. This spectrum is calculated using the real 3D code. It's noticeable that for FT2 tokamak, the positive and negative lobes of the spectrum contain comparable amounts of the input power, and therefore the spectra differ from the standard LHCD spectrum, which are shifted from one side. On the right figure, I show you the result obtained by the system of FRTC codes for current density, radial distribution. And it's clearly seen that, the current generated by lower hybrid wave takes place in the center of the machine. So the most part of the current is generated not on the periphery, but in the center. When comparing to the experiment, we make a conclusion that the result of calculation is has enough is close to experimental values. So on the left figure, I show the loop voltage drop measured in experiment by red line, and two calculated lines. Blue one is experimental plasma dense is experimental is calculated drop voltage using the experimental temperature profile, and black line is calculated drop voltage using the modeling temperature profile. It was done in order to find a good equilibrium using ASTRA code for FT2 tokamak, and we have compared how some changes in the profile influence the result. However, for both results, we see that the loop voltage drop is close to experimental one. Some small difference comes from several uncertainties. For example, as coming from Z effective that is changed during the shot and is not measured. So the value of Z effective is approximate in this case. We have performed using the system of the codes modeling for globus M2 tokamak. This is a spherical tokamak with a small radius with aspect ratio less than 2. Nowadays, it possesses the increased magnetic field and plasma current up to 0.5 megampere, operating at frequency 2.45 gigahertz for low hybrid current drive. I show some profiles for density and temperature used for simulations. And so we take these two profiles and to ASTRA code, and then calculate the equilibrium, and after that we calculate the density of lower hybrid current. The result is shown on the right side. The profiles for time positions one in the beginning and in the end of the power shot. We show the evolution. Therefore, we show the evolution of the current density profile. Here as well, we see the ohmic part of the current density, the total current density, and the lower hybrid part. And lower hybrid part takes up to 50% of the total current. Here I show the comparison between loop voltage measured in experiment and calculated using FRTC codes, and you can see the power injected to the tokamak and the total current calculated. It's clearly seen that the total lower hybrid power, lower hybrid current is about 50–60% from the total current. And I come to the conclusion. During the last 40 years, it does appear that the powerful technique to produce continuous current in the tokamak and maintain the steady state regime exists. And there are a lot of experimental results showing that the effective application of LHCD is evident, and it's possible to find these results. There are a lot of publications with it. The simulations are needed to explain the current density in the tokamak and other parameters that are not measured in experiment. And there is only one parameter to compare to the simulation is a loop voltage. I will be glad, thank you for your attention, and I will be glad to answer your questions if you have any.
Thank you for the very interesting and detailed talk. Now the floor is open for questions. Maybe I have one question myself. could you clarify what is the main difference between conventional and spherical tokamaks in case of your simulations?
The main difference is the direction of magnetic field. In a tokamak of conventional type, the direction of magnetic field almost corresponds to the toroidal direction. The angle between toroidal and direction and magnetic field is small. And in a spherical tokamak, as soon as it has D cross section, this angle goes up to 30 degrees, and it's a lot. It means that in both toroidal and poloidal directions, there is a B parallel part of the velocity parallel to magnetic field, and it has influence. It gives its impact on the total current. There are some difficulties with injection wave in a toroidal direction for LHCD. The latest approaches show that the choice should be for poloidal direction. So the lower hybrid wave should be slowed down in the poloidal direction, and our calculations show that the favorable direction is poloidal. And toroidal direction is traditional direction for injection of lower hybrid waves to the tokamak.
Thank you.
Hi, Edwin here. I have a question. I used to work with some EM permanent magnets electron machines some time back, and they were saying that the highest number that could be developed within the PMs, it's like the 1 Tesla number, which is a huge number. You mentioned that there are some magnetic fields developed there, and I guess those fields are like above the 1 Tesla limit, or it's less, or how does represents within the magnetic field?
You mean for Globus M2? Yeah, am I right?
Yeah.
Okay. So nowadays, 1 Tesla, exactly 1 Tesla is not reached, but about 0.8 Tesla is already reached. You can check the publications from 2020, recent publications from Globus M2. And could you please repeat the last part of your question concerning the LHCD?
What is the highest number of, like, what kind of Tesla numbers is being achieved within the spherical and the toroid type of tokamak? Because if it is reaching the 1 Tesla, I mean, almost, if it's going to reach it, that's going to be a significant improvement also from the magnet's perspective, because you'll have like huge amounts of strong magnetic fields there.
Okay, I understand your question, but I'm afraid I'm not the person who is competent to answer it. So I do some simulations, and maybe it's better to ask some people who work at experiment.
Oh, okay, no problem. Yeah, I was just curious because this is my first presentation that I follow right now, and I'm trying to understand so that how the low hybrid currents could be used also from the magnetic perspective of PM magnets, and generating some currents like considerably high.
So when you for lower, so how the level of magnetic field, for example, can influence the lower hybrid currents, it's clear because so we can calculate it. You see that the limit of lower hybrid wave, so there is electron cyclotron frequency. The electron cyclotron frequency is calculated using the magnetic field. So that's a direct dependency. Moreover, the profile, the magnetic field profile is used to calculate the ray tracing of the wave. So the behavior of the wave depends on both plasma density profile and magnetic field profile and temperature profile.
Gotcha. Gotcha. Okay.
I see one more question in the chat. Oh, sorry. I saw raised hand. You should be unmuted now. You can go ahead with your question.
You hear me?
Yes.
Great. So a question is that so exactly also here about the frequency. How is that in the experiment? You tune the frequency to fit to the plasma and magnetic field, or you tune the field of the plasma to fit the frequency of the source of the LHCD? How is that?
Of course, the Tokamak is a device which is rather complicated for design. That's why, firstly, the Tokamak is built, and after that, the lower hybrid grill is built. And this lower hybrid grill is built for exact Tokamak. And we calculate all the parameters to choose the grill design. So the size of the grill, it's the number of horns and so on. That's why the frequency is chosen for magnetic field and other parameters, of course.
So is that the antenna area could be slightly still modified to, because like if you like some different compositions of the ions or whatever, you need to tune anything, or did I understand correctly?
You mean the frequency can be modified?
Just I'd like to know how sensible is if like the composition of the ions is different. I mean, the Z effect is different, or the magnetic field may be slightly different. You choose another working point. How sensitive is that system? Do you need to change a lot of things?
Okay, or? Thank you. I understand the question. It's quite sensitive because firstly, when we speak about the power spectrum injected to the tokamak, so this spectrum, you see this figure in the right hand side of the slide. This is the power spectrum, and it is calculated for exact grill, for its geometric parameters and its position, and for exact density profile and magnetic field profile. And if you change the magnetic field, then the power spectrum is changed, and the peaks that you see here can be shifted. So the main peaks are usually between 2 and 5 or 7 and parallel, and these peaks can be shifted, and this changes the ray tracing. It changes the path which the wave goes inside the tokamak, and it results in changing the total current, and it results in changing the position of this total current, where it takes place, on the periphery of the machine, in the center of the machine, or how this current, what is the distribution of the current, I mean radial distribution of the current. Of course, it's sensitive, however, we need to find the range of, for example, of density for such a technique, because as you remember, the efficiency of LHCD is inverse proportional to density. So if you increase density, then the interaction will take place between the wave and ions, and it's not effective. Landau damping won't be effective, and you won't generate any current. So did I have answers for your question?
Yes, thank you for the explanation. Yeah, that's great.
I see we have a couple of more questions. Please, Huasheng, I will unmute you now.
Hi, thank you. And nice talk. I have two questions, and I said to you. The first question is how much of the effect of the H1 in the origin term in your dispersion relation is for about 10% or 50%? How much the effect can be?
The effect measured already is up to 70%. I mean, the total current can be substituted by lower hybrid current up to 70%.
Okay, okay. And the second question is, have you compared your FRTC result to the general result or secure 3D result?
There was some comparison made for JET. It was done by my colleagues, which have developed the code, and they have developed the first module of the code for JET, and the attempts for comparison between several codes has been made. So, but I have some figures for that. It was not the aim to show them, but maybe it's a good idea to include them to my future talks. And maybe to perform such a comparison for smaller machines, because the code has been modified, taking into account the electron distribution function evolution. Mm-hmm. And such an effect is new. This module is new in the code, and we can compare again. I expect this would be interesting issue. And of course, there was a suggestion to improve the code to use 2D Fokker-Planck solution module and even 3D. It's necessary for the waves, not only slow waves, but for fast wave. And because in this case, the perpendicular component of velocity is important as well.
Okay, thank you.
Thank you. We have one more question from Felicity Maiden.
I was just wondering, what is the main difference between LHCD and ECCD? Yeah, I don't think I quite understand how either work, but then what are the main advantages of LHCD compared to ECCD?
As I am concerned, the main advantage is in efficiency. However, the mechanism for all RF methods of current drive is alike. All these methods are based on the interaction between the wave and the particle. And the LHCD is widely used due to the simple approach, technical approach. It's it's not that complicated task to build a grill for LHCD, and the access to the machine is from low field side of the Tokamak. So these two methods are comparable, I can say.
Okay, thank you.
And I see one more raised hand. Please go ahead.
Hello.
Yeah, we can hear you.
All right. So I have got one information in your talk that in FTRC code, that means the ray tracing code, what has been used in your simulation work, which was first first meant for jet tokamak, and then while it was being used for Globus M2, that means spherical tokamak, there was some modification needed in ray tracing. So I couldn't clearly understand that. Could you please clarify that one in short?
Yeah, of course, it was modified. Of course, it's not used as it was built for jet. It was developed for jet 20 years ago. And since that time, it has been modified a lot. And that's separate, I call it FRTC because it's really, in reality, it's a big system of codes with a lot of modules which are written for exact machine, and the model used for jet is not the same model used for FT2, is not the same model used for Globus M2, because these machines are different. You're right. Yes, that's a good question.
So in terms of mathematics or equations, where is the difference? I mean, why was it needed to modify a main block of the code? So something like equations. So you mentioned in your one slide, I have.
Yeah. Yes, there is a slide. You mean this slide for ray tracing?
Yes, right.
Yes, I mentioned that Globus M2 tokamak is a spherical tokamak, and the curvature of the magnetic field is rather high. This introduces the curvature. This introduces some difficulties when we launch the wave in toroidal direction. It's not possible to launch the wave in toroidal direction. It won't be absorbed. This results from dispersion relation. That's why we take into account when we but the experiment shows some different results. So we faced the problem. The calculation and experiment showed different things. That's why the idea was to take into account the gradient terms which are proportional to the gradients of density and magnetic field. And these gradient terms have corrected the dispersion relation, and after that applied for Globus M2, and after that more correct equations were introduced to the code, and the result was closer to experiment.
I see. All right, so thank you for your information.
Okay, great. I don't see any other raised hands or questions in the chat. So I think that's it for today. Thank you very much for your interesting talk. I've learned a lot. And thank you for joining us today. And I wish you a nice rest of the day.
Thank you. It was a big pleasure for me to talk to you, to give a small presentation, and so I hope it raised some interest in this field, and you will learn more reading some papers. So good luck to you all.